In this video for Math 98, we will cover problems from homework number 1. These problems are like number 12, 13, 14, 15, and 16 on your homework. We'll be talking about section 11.2, which talks about the concept of direct variation. Often in life, one quantity will increase as the other increases, or vice versa, as one decreases as the other decreases. For example, think about buying gas for your car. The more gallons of gas you buy, the more it will cost you, right? And the less gallons of gas you buy, the less it will cost you. This type of relationship is often called direct variation. Here's a definition. If there is a constant k such that y equals kx, we say y varies directly as x. Notice that this is one variable equals a constant times another. No plus another constant or plus another term here. This is often referred to as linear variation. Here's another way to think about it. Notice if y1 varies directly as x1 and y2 varies directly as x2, then by that definition of direct variation, you get these two equations. y1 equals kx1 and y2 equals kx2. Now, you can divide both sides of this equation by x1 and both sides of this equation by x2. Let me just do that here. And since both of these equal k, you can equate them together. So one quick way to see if 2 points are involved in a direct variation is to try to do these little ratios and see if they're the same. For example, at a sale, 2 cans of cat food cost 98 cents, and 15 cans cost $7.35. Find the equation relating the number of cans bought in terms of the price. Well, the first thing I want to do is think about what's my input and my output. And for my input here, I'm going to have number of cans of cat food. And my output, I'm going to have the cost for that number of cans of cat food bought. So what we have here is we have a point where we say 2 cans bought is 98 cents and 15 cans bought is $7.35. Now, according to this right here, if I can just set up a variation, I'm going to look at 0.98 over 2 and 7.35 over 15. Are these the same? Well, I'll go over to my calculator and I'll figure that out. 0.98 divided by 2 is 0.49, and 7.35 divided by 15 is 0.49. So yes, these are the same. And in addition, 0.49 is this constant of variation. So I could write my equation as y equals 0.49x. So this gives me a direct variation. We could say y varies directly as x, or the total cost of cat food is 49 cents times the number of cans that we buy. So that's an example of direct variation. Now I want you to understand not everything is direct variation. Let's take a look at this problem right here. Repairing a 12-foot sidewalk takes 12 hours. The same contractor takes 17 hours to repair a 32-foot length sidewalk. Let's try to think about whether this is direct variation or not, and whether this is, and whether we can find an equation relating this. So for my input, I'm going to have the length of the sidewalk that I'm going to repair. And for my output, I'm going to have the number of hours. Now it doesn't really matter which one's input or output, but that's just the way I'm going to choose this. So I'm going to call my length of my sidewalk L, and I'm going to call my number of hours H. So in my first case, I have the pair. My input is 12 and my output is 12. And my input on the second one is 32, and my output is 17. Okay? So if I do this here, if I do that ratio again, 12 over 12 is clearly equal to 1, and 32 over 17, okay, is not equal to 1, right? So 32 over 17 is something larger than 1, so that these are not equal. So this is not direct variation. So how would I find an equation? Well, you might remember from Math 93 or 92 that you have 2 points here, and I'm going to find a slope of the line. If I wanted to find a linear line, I would calculate the slope, and that would be 17 minus 12 over 32 minus 12. 17 minus 12 is what? It's 5, and 32 minus 12 is 20. So this is 1/4. So that's my slope. And I could say y equals mx plus b if I wanted to fit a line through these points. And I'd say y equals 1/4 x plus b. Now I don't have the y-intercept here, but if I wanted to fit a line through these points, I could now plug in one of these points and solve for b. So I might just choose 12, 12. And this is going to give me 12 equals 1/4 times 12 is 3 plus b, so b equals 9. So my final equation relating these 2 points is 1/4 x plus 9. And you could check that and see that that actually does work as a relationship for this. But this is not direct variation because of this plus 9 here. Notice that this has this 1/4 x plus 9, and that's not direct variation. If I had something like this, it would be direct variation. Let's look at some problems from WebAssign. Let's start with this first one right here. I'll zoom in just a little so you can see it. A 6-pound weight stretches a spring 2 inches. A 15-pound weight stretches the same spring 5 inches. So we would like to find out a relationship between these two. I'm just going to let x be the 6-pound weight, so I'm going to let x be the weight, and the y be the stretch of the spring, okay? So let's see, is this direct variation or not? So I'm going to take y over x, so I'm going to take 2 over 6. Is that the same thing as saying 5 over 15? If you look at these, you'll see that both of these are 1/3. 2 over 6 and 5 over 15 is 1/3. So those are equal. So my equation is going to be y equals 1/3 x. Okay, so if I plug in the value 6 here, I would have 1/3 times 6, or 2. If I plug in the value 15 here, I would have 1/3 times 15, or 5. So this relationship is direct variation. Another problem, and I'm going to have you try to solve this yourself. Tax on a purchase is $120, and tax on an $18 purchase is $135. So we want variables for input and output, and then decide whether we have a linear equation as direct variation or not. You can start the video again once you have finished. Okay, because it's typical in real life the way we do this, I am going to let x be the purchase price, and I'm going to let y be the tax. So I'm going to do that. We're going to do y over x, so I'm going to take 1.20 over 16, and I'm going to compare that to 1.35 over 18. And let's take a look. Use your calculator. 1.20 divided by 16 is 0.075, and 1.35 divided by 18 is 0.075. So do we have direct variation? Yes, we do. And this value here is that constant. So y equals 0.075x. And again, you can check that. You could plug in the purchase price 16 times 0.075, and that would give you $1.20. And you can take 18 times 0.075, and that would give you 135. So this relationship is also direct variation. Now, in all the examples we have done so far, this has been linear variation. Is it possible to have other types of direct variation? And the answer is yes. Another type of direct variation is called quadratic variation. If there is a constant y equals k times x squared, we say y varies directly with the square of x, and k is called the constant of variation. Some examples from real life that you might know. What is the area of a circle? You probably know that the area of the circle is pi r squared. Well, here's the input and here's the output, and you could say that area varies directly as the square of the radius. Give you an example. If I have 2 inches for my radius, my area is pi times 2 squared, or 4 pi. And if I have 5 as my variation, I would have pi times 5 squared, and that equals 25 pi. So this is an example of quadratic variation. Another real-life example of quadratic variation is surface area. Let's take a look at this. Here I have a cube. Surface area of a cube varies directly with the square of its side. So if I just didn't know the formula, but if I wanted to figure it out, I could say A equals K times the square of the side, where A is the area and S is the side. And here I could say, well, look, I've got K times 2 squared, okay, which is going to be, what is that? That is 4. And here I'd have area equals K times 3 squared, which is K times 9. And in both of these cases, we know that there are 1, 2, 3, 4, 5, 6 of these. So each side has area 4 squared in the first case. And so the area would be 6 times 4, or 24. And the area here would be 9 times 6, or 6 times 9, which would be 54. And so that gives me another example of where I have quadratic variation. So area in general for surface area in general for a cube is 6 times s squared. Okay, let's take a look at some kind of interesting problems here. Here's a table. Okay, so this again is from WebAssign. Here's a table, and it tells you that this is an example of direct variation, but it doesn't tell you if this is linear or quadratic. How can we tell? Well, if it were linear, look at this problem one and this one. In this case, we have P and W. So making P my input and W my output, I would have to have 12 over 4, which would be 3, and 75 over 10, which would be, what, 7.5. So this is not linear. Now, since I either have to have linear or quadratic, I know that this has to be quadratic variation. Okay, so to find that equation, I'm going to use my general equation here, my output being W and my input being P, and you know that this is quadratic variation, so W equals K times P squared. Okay, and you could say, well, okay, I'm going to pick one of these points, either 412 or 1075. Those are the only 2 points where I have both of them. Just for fun, let's pick 1075. Let's say 75 equals K times 10 squared. So that gives you that K equals 75 over 100. 75 over 100, what is that? Well, if you reduce that fraction, you get that k equals 3/4. So W equals 3/4 times p squared. Now, the rest of the problem, that's my equation of variation right there. The rest of the problem asks you to solve this using this equation. So, let's look at the ones where we're given p and we're not given w. Those are easier to do first. I could use 7. If I plug 7 in here, I get 3/4, okay, for this one, 3/4 times 7 squared. So that's 3/4 times 49. And 49 times 3 is 147, so this one is 147 divided by 4. For 12, I would have 3/4 times 12 squared. Well, 12 squared is 144. And remember, 3/4 times 12 squared is going to reduce to 108. So this is 108. For these, you could solve for p, and remember in the original problem it said p is greater than 0. So let's look at this first one. This first one, I would have w equals 3/4 p squared, and w is going to be 3. And you guys are experts at solving equations, so you multiply both sides by 4/3. This gives you 4 equals p squared, so p equals 2. Now, you could do the same for this problem for 147. Here's a problem I'd like you to try to work out on your own. It's very similar. The following table is an example of direct variation. I'm going to assume q is greater than 0. So I want to know, is this linear or quadratic? I want to find the equation and then complete the table. Now, I'll give you a moment to figure this out yourself. You should pause the video and then continue when you are ready. Okay, to check direct variation, I'm going to say this is input and this is output, and I have 9 over 100, and I have 90 over 1,000, and you can see that these two ratios are exactly the same. So therefore, this is direct variation, and your constant of variation is 0.09, or 9 over 100. So we are linear direct variation. My equation would be r equals 0.9 times q. And now let's just do this. Okay, if you would like to kind of do this on your own, if you have a moment to do that, you certainly can. Pause the video now, but otherwise we'll just kind of do this. We'll say 20 times 0.09. This gives me 1.8. And 100 times 9, we've got that one here. 1,400 times 0.09 gives me 126. And for these, pretty easy. You could say 3.6 equals 0.09 times q. So q equals 3.6 divided by 0.09, which is going to be 40. And 67.5 equals 0.09 times q. And again, 67.5 divided by 0.09 is 750. I hope you found this video useful.